Hey everyone, welcome back to Linear Algebra. This will be part B of lecture 19. And where we left off, we had just discussed how to coordinatize a vector and what coordinatization meant, and done a few examples of using row reduction to coordinatize a given vector along an ordered basis. So now we want to kind of explore further applications of this and see some more examples and think about how we might expedite some of the computation here. And so the next thing we'll look at is how is it possible to convert between bases, right? So given a vector that's coordinatized in a particular basis, given a vector that represents a coordinatization in a particular basis, how can I transition to a different ordered basis, coordinatization? And so let's talk about that here. This is kind of a heavy definition here, but let's just write it out and then we'll break it down. So suppose that V is and we're going to say non-trivial, right? So not a simple vector space, not the zero vector space, but suppose that V is a non-trivial n-dimensional vector space with ordered bases B and C. All right, so I've got two bases that are ordered and are bases for this non-trivial n-dimensional vector space V. Okay, so we're going to let P be an n by n matrix. We're going to let P be the n by n matrix whose ith column for 1 less than or equal to I less than or equal to n equals bi coordinatized in C, where obviously, I mean, you can imagine bi is the ith basis vector from B. Okay, and so if P is a matrix set up like this, then P is called the transition matrix from B to C. Okay. Okay, so this is called in this case, P is called the transition matrix from B to C. Now, some notation that is sometimes used would be like this: P from B to C. This is notation that I've seen people use before, which I think is convenient. Okay, and so frequently we'll just call P the transition matrix from B to C, right? So we don't have to say it's the transition matrix from B coordinates to C coordinates. We can just say it's the transition matrix from B to C, knowing that that means a coordinatization, of course. Context here, right? Okay, let's see an example of this. Let's see if we can generate one of these. Okay, so we're going to let U2 be the upper triangular matrices, and we're going to consider the following two bases. Consider the two ordered bases, right? And so we'll call the first one B, and bear with me, I have to write these out, but it's going to be 7300 1 2 0 negative 1 and 1 negative 1 0 1. Okay, so that's the first order basis B, And then the second one is what we would kind of think of as the standard ordered basis here. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. Okay, so C is kind of the more standard one. B is something else. Both of them are bases, though. Both of them can be used to represent any upper triangular matrix. Now, for the items in B, we can pretty easily calculate the C coordinates, right? So for the items in B, we can easily calculate the C coordinates. How do we do that? Well, you can pretty much just look at them in this case. They're pretty straightforward, right? So let's do this first one, for example. So 7, 3, 0, 0. In terms of C, that's just going to be 7 times 1, 0, 0, 0 plus 3 times 0, 1, 0, 0 plus 0 times 0, 0, 0, 1. Right? And so 7, 3, 0, 0 coordinatized in C is equal to 7, 3, 0. Right? That's straightforward. We can do the same thing for the other two as well. Right? So this one, I'll say also, I won't do these all explicitly, but I'll just write them down. You can confirm this. 1, 2, 0, negative 1, coordinatized in C is equal to 1, 2, negative 1. And this last one here, 1, negative 1, 0, 1, coordinatized in C is equal to 1, negative 1, 1. Okay, so we've got those three. Okay, so the key thing here is that I've got this one, I've got this one, and I've got that one, right? And so if we go back to the definition of the transition matrix, what does it say? It says a transition matrix is going to be the n by n matrix whose ith column is equal to the transition of the ith b vector under the C coordinates. Right, so that's what we have here. This is the first vector from B coordinatized in C. So this would be the first column of P. This is the second basis vector, right? 1, 2, 0, negative 1, 1, 2, 0, negative 1, coordinatized in C. So this would be the second column of the transition matrix, and this would be the third. Okay, so then the transition matrix, and we'll call it P from B to C, is P from B to C is equal to, again, 7, 3, 0. That's the coordinates of the first basis vector in C, in B under C, and then 1, 2, negative 1, that's the coordinatization of the second basis vector in B under C. And then 1, negative 1, 1, that's the coordinatization of the third basis vector in B under C. Right? So this is the transition matrix from B to C. Okay, that's the transition matrix from B to C. Okay, so what's the use of this? Well, the next theorem shows us how we can use this to go from a coordinatization in B to a coordinatization in C. So the next theorem shows us how P, B to C, can be used to go from a vector coordinatized in B to the same vector coordinatized in C. Now, obviously, you could just back out of the coordinatization and just redo it in C, but P can be used instead of that method, and it's significantly more efficient. Okay, and so theorem. Suppose that B and C are ordered basis. for a vector space V. Okay. Now, technically, V needs to be n-dimensional. We know that. We're talking about finite dimensional vector spaces. And it should be non-trivial, right? Meaning it should be more than just the zero vector. And let P be an n by n matrix. Okay. Now here's the punchline. Then P is the transition matrix from B to C if and only if for all V and V, for all vectors V in the vector space V, P times the vector space, or sorry, the vector coordinatized in B is equal to V coordinatized in C. Right, so basically what this says is that the transition matrix can be used, you can just do a multiplication by the transition matrix and you get the new coordinatization. It's just that easy. Okay. That's extremely convenient and very powerful. Okay. Let's see an example here. Let's see an example. Okay, so let's consider ordered bases B and C. So B we'll say is equal to 12, 9 and 15, -1. And C is equal to 3, 4 and 6, 1. All right, so two obviously different ordered bases. Okay, so if I want to coordinatize this guy in terms of C, what I can do is I can set up an augmented matrix, 3, 6, 4, 1, and then 12, 9. And I can row reduce that, and I get 1, 0, 0, 1, 2, 1. Okay, what does this mean? Well, that implies that 12, 9 coordinatized in C is equal to 2, 1. And we talked about what this is. We did this previously. I can do the same thing for this other vector. So 3, 6, 4, 1. I want to coordinatize 15, -1. That row reduces to 1, 0, 0, 1, and then -1, 3. Okay, and so that means 15, -1 coordinatized in C is equal to -1, 3. Okay, so we've got that. And so given this, we can generate a transition matrix. So the transition matrix, and we'll call it P from B to C, is equal to 2. So it's these two and this 2. So 2, 1, and then -1, 3. Okay. All right, so we flip pages here and we can talk about what this is. So I've got P from B to C, and I'm saying that's equal to 2, 1, -1, 3. Okay. Now let's consider a random vector in R2. And I'll just say 339 is the vector in R2, right? Right, so it's in the vector space. Well, it's in R2, and I've checked it's in both of the vector spaces spanned by B and C. So we can calculate so what we're trying to do is we're trying to show that this transition matrix can be used to move from a coordinatization in B to a coordinatization in Z by simply multiplying. Right, so what I want to do is I want to take a random vector and I want to coordinatize it separately and then show that the multiplication works. So I can coordinatize 339 under B using row reduction. So I take 12, 15, 9, negative 1. So these are the vectors from B, the basis vectors from B, and I can row reduce this system. And I get 1, 0, 0, 1. Again, pause the video, make sure this is all making sense. This is kind of computationally heavy, so I'm ripping through it. Right, so I can get to that. Okay, right, and so 339 coordinatized in B is equal to 4, negative 3. I can do the same thing in C. I need to do these separately, right, so that I can show that the multiplication works. And so doing it in under C would be 3, 6, 4, 1, 339. And that row reduces to 1, 0, 0, 1, 11, negative 5. So 339 in C is equal to 11, negative 5. Okay, and so we've got this. Now, what the previous theorem said is that, hey, if I've got a coordinatization in B, I can multiply it by the transition matrix, P from B to C, and I should be able to get the coordinates. The product should be the coordinatization in C. Okay, so let's try that. So I'm going to start with PB to C. I'm going to let me write all this out here first. So what's the plan? Transition matrix from B to C, I'm going to multiply against the coordinatization in B. So where I start, right? So I'm going to multiply it by the coordinatization in B, and what I should get is the coordinatization in C. Right? So if I take this guy here, and I multiply it by this, I should get this. So let's see. 2, 1, 2, negative 1, 1, 3 times 4, negative 3 equals, and do the math here. So it's 2 times 4 is 8, plus 3, 9, 10, 11. And 4 minus 9. Sorry, hold on. Yeah, so then you get negative 5. Yep, 4 minus 9, negative 5. Okay, right. So look, this is equal to what we wanted, and these were found separately, right? So once I find the transition matrix, I'm done. I don't have to row reduce anything ever again. I just can multiply. And so that's the long and short of it. So that's what we've showed here in this example. We started with a vector coordinatized in C, namely 4, negative 3 is the coordinatization. And if I multiply that, that's the coordinatization in B. If I multiply that by the transition matrix, I get a new coordinatization. And we confirm that by independently sort of finding the coordinatization separately. Very cool. Okay, all right, so very cool. That is the idea with the transition matrix. Now, the transition matrix depends upon identifying, taking all of the basis vectors and coordinatizing them, right? So this can also be, there are also more efficient ways to do that, to do that work. And so let's talk through what that looks like. Okay, so it is also possible to calculate the transition matrix using row reduction. So how do we do it? So to find P, the transition from B to C, we want to start by setting up an augmented matrix. Okay, and it's going to be basically your C basis on the left-hand side and your B basis on the right-hand side. And then we want to row reduce this augmented matrix and remove the 0 rows from the bottom. Okay, I mean, all of this stuff kind of fits together, right? I mean, it's basically the same idea as like if I'm coordinatizing a particular vector, then I can just use a system. Well, all I'm doing here is simultaneously coordinatizing every vector in the basis, right? That's all that's happening here. Okay, and so, here's, given like the previous example, right? The previous example I had, so from the previous example we had what? We had B, the ordered basis was 12, 9, and 15, negative 1. And C, the ordered basis was 3, 4, and 6, 1. Okay, so if I want to find P from B to C, I can just use this method, right? I need my C basis and my B basis. Okay, and in this case, that's just what? That's 3, 6, 4, 1. And then the other side is the B basis, so 12, 15, 9, negative 1. I need to row reduce that. Okay, when I do that, these are all basis vectors, right? When I do that row reduction, I get 1, 0, 0, 1. And then what I get over here is 2, negative 1, 1, 3. I did this operation separately for 12, 9, and then separately for 15, negative 1. And you'll notice, if you look back, we got 2, 1, and we got negative 1, 3. Well, all this is saying is I can do it all at the same time. I don't have to do them separately. So when I do that, I have P is equal to this. So 2, negative 1, 1, 3. Which is what we found previously. Okay. Okay. All right. Okay. So now we know what a transition matrix is. We know how to easily find transition matrices. When I say easily find, I just mean we know like a method that's straightforward. Row reducing matrices isn't necessarily easy. But it's something that we all know how to do. It just might be computationally intensive. So we could use a computer. But we know how to do it is the point, right? It's easy to think through how to do it, and that's kind of the key here. So we talked about how transition matrices can be used to transition from one coordinatization to another. Right? Now, what happens if we want to traverse multiple coordinatizations? And we want to use the transition matrix. How does it all relate? What happens if I want to go from B to C and then to D? How can I use the transition matrices to do that? Okay, and so here's the theorem. So suppose B, C, and D are ordered bases for a finite dimensional vector space V. I'm just going to put for a vector space V, but know that these V is about finite dimensional, non-trivial, and finite dimensional. And let P, I'm going to write it out like this, so let P be the transition from B to C, and we're going to let Q be the transition from C to D. Okay. Then the theorem says, then the product Q times P is going to be the transition matrix from B to D. Killer, right? So I can move through multiple coordinatizations by simply multiplying the transition matrices like this. Right, now notice that the transition from B through C to D can be accomplished using P and Q, but we do have to multiply them in reverse order, right? You would think that P would come first since I go from B to C first, and you would think that Q would come second, But in actuality, it's the reverse, right? But you can kind of think of it like this. You know, if I have a vector v that's in a b coordinatization and I want to multiply it and get it out of that and into d, then I have to multiply it by qp, right? Now, v is going to get multiplied by p first, and then it's going to get multiplied by q. So you can kind of think of it like this. V has to go through p to get to q, right? Even though when we look at this product, we say q comes first and p comes first, but in reality, p is the one that's closer to v, right? So keep that in mind. But that's going to yield us a coordinatization of v in the basis vectors d. Okay, so this is a really nice idea. Really convenient. As soon as you get over the the reverse nature of the matrix product, I think it doesn't get much nicer than this, right? So let's think about, let's take this to some extremes here. So let's say I've got S is going from A to B, and I know realize I'm kind of abusing function notation here, but that's okay. And let's say that T goes from B to C, and let's say that U goes from C to D, and let's say that W goes from D to E. So if I want to go directly from A to E, you know, I can use a product of these matrices. I can use the product. So to go from A to E, that means I have to first hit A's matrix, and then I hit. So I first hit the matrix to go from A to B, and then I hit the matrix to go from B to C, and then I hit the matrix to go from C to D, and then I hit the matrix to go from D to E. All right, so this is just one matrix. Calculated once, you can do a whole vector space using just this one matrix. So V coordinatized in E is equal to the matrix product WUTS times any vector coordinatized in A. All right, so that's really cool. That's really cool. And we've got a number of examples that you could easily configure to test this out on. So take like the previous example with the subspace of R2, and then just throw in one additional basis vector. You can just use a standard basis vector, and you could do an example pretty quickly using that. Excellent. One last theorem, and this is a beauty also. This one is kind of almost, maybe not the punchline, but it's, you know, if there was going to be a best theorem from this section, this one might be it, just because it is so aligned with what you would like it to be. Like if I said to you at the onset, hey, I've got a transition matrix from B to C, what do you think the transition matrix from C to B is? I bet you can guess what this theorem is going to say it is, right? I mean, just what would you most like it to be? That's what it is. So let's let B and C be ordered bases for V. And let P be the transition matrix from B to C. Okay. Then P is, here's the word that'll really clue you off, non-singular, and P inverse is the transition matrix from C to B. Okay, so if I've got a transition matrix from B to C, it's definitely invertible, and its inverse is the transition matrix in the opposite direction. And in hindsight, you know, maybe this is obvious by the previous examples where we were finding transition matrices and kind of the way it was used. You know, when we said you could, you know, take the first basis, sorry, when you said you could take the first basis and the second basis, row reduce it, and you get 1, 0, 0, 1, and then you get a p. Right? Well, obviously, if you flip this around, do the same operation, you better get p inverse. Right? So that's, I mean, in hindsight, it's like sort of obvious when you look back on that, but maybe you didn't see it coming. I didn't see it coming the first time I came across this, and I thought that was pretty clever. Okay, so let's do an example here. This will be the last example. Let's just take a look at what this looks like. So we're going to revisit our R2 subspace here. So let B equal 12, 9, and 15, negative 1, and C equal 3, 4, and 6, 1. And let's calculate the transition matrices. Okay, so we'll start by calculating P from B to C. Okay, and how are we going to do that? Well, we have to use this setup, right? We take C, augment with B, and then row reduce. So that's 3, 6, 4, 1, and then 12, 15, 9, negative 1. And you can, again, pause the video, double check that this works. I'm not just making this up. And you can see that obviously we get to that. We've seen this though, this is not new. Let's look at, what we haven't looked at is Q, which would be the transition matrix from C to B. So we can also calculate that separately. Now, the theorem says that it's merely the inverse of this, but let's check, do it the other way. So let's calculate Q, which we would call the transition matrix from C to B. So here it's just kind of flip the order here, right? So 12, 15, 9, negative 1, and then 3, 6, 4, 1. Row reduce that. And we get something that's not as pretty, but it's fine. So we get 3 sevenths, 1 seventh, negative 1 seventh, and 2 sevenths. So we get that. And so, right, so up here, sorry, let me double check that I make sure that this, let's put the actual numbers here. So 2, negative 1, 1, 3, that's the transition matrix P. Okay, and Q now we've calculated is this other thing, 3 sevenths, 1 seventh, negative 1 seventh, and 2 sevenths. Okay, so all that's left to confirm is that this is the inverse of that, right? Is Q the inverse of P, and vice versa? How can we tell? Well, the way we can tell is, the way we've done it in the past is we say, okay, like if I want to know the inverse of P, I can set up an augmented matrix with P in it, and with, in this case, a 2 by 2 identity on the other side, and I can row reduce it. Okay, and so doing that, what do I have? I have 2, negative 1, 1, 3, and then the identity over here, right? And if I row reduce this, then once it's in reduced row echelon form, whatever's over here is the inverse of P. And you'll never guess what is there when we put this in reduced row echelon form. 3 sevenths, 1 seventh, negative 1 seventh, and 2 sevenths. All right. So Q is equal to the inverse of P. Okay, and so that's kind of the big, the nice reveal here at the end. So perfect, that's what we were expecting, right? And again, double check the calculations, all these ... sections here, make sure you know. These are simple 2 by 2, so it should take you only a minute or two to calculate it. Or get out Wolfram Alpha, load it up on the desktop, and just dial the matrices in and have it do the grunt work for you. But confirm it. But yeah, you'll see that the transition matrices are basically inverses of one another. Going one direction, it's P, and going the other direction, it's inverse of P. So very nice. All right, so that's where we'll leave it for this section. Next time we get together, we will be switching gears again. So lecture 20 will move forward into a new section of linear algebra, which we'll just term linear transformations. And so we'll get into that next, and it'll be a lot of similar ideas, or ideas from vector spaces that will be recast in different contexts. So, anyways, we'll talk to you all then. Take care. We'll see you next time.